Is rather important differences between the simple male, what happens in the female. We talked about the early germ cell propagation in the female, but the stages at which the female begins to undergo meiosis are very different from what's over here in the male. So lots of those oocytes are stalled in meiosis 1 for prolonged periods of time, and they take triggers, either chemical trigger, biochemical triggers, endocrinologic triggers, or actual cell-cell interactions to move from one stage to another. So these cells can't go on to full completion of meiosis until after puberty. So until after you have estrogen available, FSH and LH in fluctuating levels available, the support of the surrounding cells, unless that's available, all of these cells, if you start a cell here that's in diplotene, essentially at the prophase of meiosis 1, and you start moving toward development, all of the developing oocytes to this point are lost because there's not endocrine support of their further development. So once they begin entering meiosis, you get production of the first daughter cell other than the oocyte itself. Notice how asymmetric the division is. So these two are the two end products of meiosis 1. This diagram in here is meant to include what happens in canids or canines, which actually require sperm interaction for completion even of meiosis 1. Most other species, it's just the endocrinologic support of growth of the follicles that allow movement to the completion of meiosis 1 and the production of the first polar body. This is 2N at this point, this is 2N at this point. It's not until after ovulation, removal from the ovary, that you see this cell being in a condition that it can complete meiosis, both enter and complete meiosis 2. So you get to meiosis 2, prophase, and this is the stage at which interaction with sperm, actual ovulation, actual fertilization occurs. This is the status. So you've got an agate, finished meiosis 1, prophase meiosis 2, a polar body, and these are all inside the zona pellucida, which is this carbohydrate rich protein coat that surrounds the egg and the polar body and this space, which is called the pyramidal space, where sperm actually interact with the egg. The sperm interaction with an egg causes a pulse of calcium to be propagated from the point of contact. It actually goes out. It goes out and it sometimes rings. That is, it goes across like a wave and bounces back once or twice. And you'll see what that calcium wave does. But one of the things it does is to stimulate the egg to complete meiosis 2, so that it forms the female pronucleus and extrudes the second polar body. The second polar body is one end. This is now one end. You sometimes get coordinated division of the first polar body to form a third polar body out here, at which point this would be one end and this would be one end. In rare circumstances, you can also get fertilization of the first polar body. In those circumstances, remember they're all in the zone of pellucida. What often happens in those circumstances is you get a chimera formed in which the growing embryonic cells of this mass get fused with the embryonic cells of this mass. And you would only pick that up if for some reason there was a difference, say a mutation that showed up here that didn't show up here. And it would show up as an isolated raft of cells or an organ within the organism, the afterbirth, that was genetically different from the rest of the organism. Okay, so the main thing I'm getting to you, or trying to get to, is the fact that meiosis is not complete in the female until the time of fertilization. Very different from what you see in the male. So what about all the eggs? Oogonia is developing female germ cells. Prior to birth, you're getting mitotic replication, and the numbers in a human, for instance, would go up to several million, maybe as many as 3 or 4 million. And those would be located in an area called the indifferent gonad. The gonad hasn't fully developed at that point. And at some point, they'd cease active division prior to birth. And they'd enter meiosis I prophase. So by the time of birth, you've got a number of those cells that have tried to go beyond that meiosis I prophase, but because of a lack of endocrine support, they're lost. So by birth, you're down to numbers that are maybe a couple million in the ovaries. Okay. Following birth, you're going to have a childhood that extends out to about this stage. And all during that period of time, there are a certain number of oocytes that are going to attempt to begin to resume meiosis. But again, the endocrine support isn't there until you hit puberty. And it's only after that that you're going to actually support the production of oocytes that are mature and capable of fertilization. So by this time, you're down to something like 500,000 cells. By the time you get to the cessation of ovarian function, and in primates, menopause, the cessation of menstrual cycles, the end of the active reproductive time, you're already down to a couple of thousand oocytes. Okay. So you can see that between here and here, there's a limited number of cells that are actually going to be going on to potentially form fertile eggs. Now, a little math in biology doesn't hurt.
Yes, it does.
No, it does not. Okay. Now, puberty occurs at what age?
You just ruined it.
11 to 9.
Puberty at 9 is a little young.
12?
Somewhere around 12 years of age. Menopause occurs about when?
40s?
40? 50.
It's somewhere between 45 and 50 on average. So let's say 50. Okay. How many years is in between?
Oh, no, man. Wow.
Come on, how many years have you played? 38.
Oh, is this the math?
Okay, now, how often does a female ovulate? A primate ovulates? Every 30 days.
21
It's actually between 28 and 30. 29 is a good mark. But if it's 29 days, how many ovulations occur during a year? A solar year. About 13. Okay? So 13 menses per year. Somebody do the math, please. 3 times 8.
8. 494.
3. 494.
If I calculated it.
Yes. Okay, so about 500 cycles during a reproductive lifespan. How many, and that's without a pregnancy present, how many eggs are normally shed during one cycle? In primates. Well, it's a little over 1, but it's 1 to 2. And let's say even 1.5.
Oh, nice. Because twins aren't usually from dual fertilization. It's from fertilization of the same egg, right? Not separate.
Yeah, they're often splitting of the embryo after fertilization. Yeah, well, actually, it depends.
Or fraternal.
Depends on whether you've got fraternal or paternal. Or paternal or not maternal. Identical or identical. Oocytes. What's 1.5 times 500? 750. 750 potential eggs during a reproductive lifespan. Okay? We're up here at what, 100,000? More than 100,000. We're at several 100,000 here. And we're down to 1,000 here. Is that number anywhere close? Okay? So the vast majority of potential oocytes are lost during reproductive life. And it doesn't matter whether you're a primate or a mouse. The same thing is true. About 99% of oocytes are lost by missing the endocrine signals, missing the windows in the endocrine patterns during reproductive lifespan. Okay, a little on ovarian anatomy. I think I showed you this before. This is the gross anatomy. This is the ovaries of a cat. There are 2 of them here. This one does not have follicles, active follicles growing. This one has a preovulatory follicle that occupies a substantial proportion of that ovary. And at the top, you see a regressing corpus luteum, which would originally have been about the size of that preovulatory follicle following ovulation. Okay. In a human, in a primate, those ovaries are about the size of your thumb. And the preovulatory follicles at their most mature point are between about 3/4 of an inch and an inch in size. Okay. If you cut these through, or section through them, what you're going to see is this structure. One of the things to note is that most of the follicle growth is actually occurring right under the shell or the outer rim of the ovary. It's the cortex. That's where the ovocytes and the follicles are going to be located. And you're going to see follicles of a whole range of different sizes, ranging from real tiny ones that you can barely notice to ones that are just about the time of ovulation, like this one. And the ones that look empty, these, well, this one not so much because there's the oocyte. This one, the reason that looks empty isn't because there's anything wrong with it. It simply means where you made the cut was off center. It didn't cut through the oocyte. So, these various stages of follicles, most of what you're seeing in here is what's called stromal tissue. You've got a lot of blood vessels, and you've got nerves also coming into here. And these come out through the hilus, this area where it attaches to the rest of the organs, largely via the capillary, or the blood vessels and the nerves. Over on the other side here, come on, there we go. This is an ultrasound of a follicle, pardon me, of an ovary during the cycle. And one of the things you're going to see are what look like hollow spaces. Those are the follicles growing. The fact that you can see them with an ultrasound or ultrasonic probe simply means that you can follow the growth of a follicle by taking serial ultrasounds. And that's actually one of the things that's done if women, for instance, are being stimulated, or cattle are being stimulated in preparation for in vitro fertilization or insemination, artificial insemination. This is a picture blown up further showing you a preovulatory follicle. A big hole in the middle of that ovary. Okay. This is a depiction of the growth of a follicle through several stages. It starts out with what amounts to the early stage oocyte surrounded by a few flattened cells that are going to ultimately develop into granulosa cells. As it goes along further in development, come on, you're going to see these cells begin to proliferate, and you're going to see growth of the oocyte. And you're going to see formation of what looks like, almost like another cell. What that is the oocyte's nucleus, and it has a very clear nucleolus as well. You're starting to see the formation, notice this clear space. That's beginnings of formation of the basement membrane, which separates this structure from the vascular elements in the ovary proper and makes this space avascular. Later stage, you're going to see more continued proliferation of the granulosa cells, growth, major growth of the oocyte, and you're starting to see the cells immediately surrounding the basement membrane develop into the thecal cells. The thecal cells, as you recall, coordinate their production of steroids with the granulosa cells. So the end product is estrogen, which is needed to drive development of this whole structure and to help control central production of LH and FSH. Where are you? As this continues forward, you see again more proliferation of granulosa cells, more differentiation of the thecal elements out here. You start to see fluid building up in the space here. This is called the antrum. This particular follicle is a little abnormal or unusual, because there are actually two oocytes present in that same follicle. And you can see them right there and right there. And around each one, you start seeing a kind of a collection of what look like fairly early stage granulosa cells. Those are the cumulus granulosa cells. The rest of these things are mural granulosa cells. These cumulus cells respond to FSH, but they do not respond to LH. But ones outside here begin by responding to FSH, and one of the things they do in response to FSH is make the receptors for LH. So these are the ones that end up responding to LH later on. When you're just before ovulation, you're going to see structure that's, again, a lot larger, more granulosa cells, both of mural type and cumulus type, and you're going to see more protein sedimented in the center, or not sedimented, deposited in the center in the antral space. This particular section was not done very well histologically, because this space, you see this white area, is not really present. It's an artifact of shrinkage during preparation of the slide. So this stuff would extend all the way to the granulosa cells out here. Follicles are very sensitive to endocrine conditions, and if this particular growing follicle doesn't get enough LH or enough FSH at the appropriate time, one or more of these granulosa cells are going to enter apoptosis. And once one starts to enter apoptosis, they all do, and the follicle fails. Part of that is because all of these granulosa cells in these follicles communicate with one another by something called gap junctions. What are gap junctions?
Connections between cells that allow for passage of material.
Okay. They are membrane specializations that allow passage of molecules up to about 1,000 molecular weight from one cell to another. How do those differ from tight junctions?
Tight junctions hold cells together and, or hold them down to a basal membrane. You can't, I don't know, something past the
Okay. Tight junctions are not communication junctions. They're sealing one cell to another. The best example I can give to you,
the basal lamina.
well, not the basal lamina. The best example I can give to you is what happens in blood-brain barrier, the blood-testis barrier, where those junctions form something almost like a Ziploc seal, okay, that holds fluids from the outside from penetrating into a luminal space, like the antral. But in those instances, you're sealing one compartment from another. In the gap junctions, you've got one cell over here, another cell over here, so cell 2, cell 1, and in between, you have proteins in each membrane that help to form a channel, an actual cytoplasmic channel between the two cells. So things like cyclic AMP, calcium, potassium, etc., can move from one to the other. So if you trigger this cell with a hormone, you'll often see this cell responding as well. Okay, so follicle growth. What happens after ovulation? Well, you lose not only the oocyte during at ovulation, you lose the surrounding cumulus granulosa cells. It's called the cumulus oocyte complex. And the rest of this structure, the granulosa cells, the thecal cells, have a morphological change, great morphological change. These cells are relatively small. They have a large nucleus relative to the amount of cellular space, relatively small cytoplasm, And they have they do not have a distinct nucleolus. But as they convert to the corpora lutea, you see a real transformation. You see them form fairly robust cells with a very distinct nucleus and a very distinct nucleolus. Okay? So these cells are amped up to make proteins, they're amped up to make steroids. Because the other thing you see, if you look at these under, for instance, transmission electron microscopy, is you'll see a lot of smooth endoplasmic reticulum. And you'll see specialized mitochondria that are particularly devoted to the production of steroids. Now, you may have run across this particular image in a variety of places. It's been on the web, it's been in publications for, 35 years now. And some people have labeled it as a primate or a human follicle. It is not a primate or a human follicle. This was an image, a scanning electron microscopic image of what's called a freeze-fractured follicle. So this structure was fixed and fractured, broken open, and then coated with a metal and put under a scanning microscope. And this particular image was fortuitously captured. The guy who did it was Paulraj Bhagavan Das. He was working in the same lab I was at the time he did this. This is a rat follicle. Okay. A mouse follicle or a rodent follicle would look similar to it. The reason we know that, and we can prove it, is that the mural granulosa cells in rodents pile up in multiple layers. And in most other species, you have fewer layers of cells. So in ruminants, there's maybe a couple of cell layers above the basement membrane that you can see. And you'd see that in primates as well. So the thickness of the layers gives it away, but it does show very well the mural granulosa cells, the cumulus granulosa cells, there's the oocyte inside, and then there are thecal cells that are piled up outside. Okay. Now, we come to a bit more of the ovarian physiology, the psychophysiology. You want to know all about the controls of follicle-stimulating hormone and luteinizing hormone. We've been through that already. Okay? But the pattern over time is not something we've really dwelt on. In a primate, it doesn't have to be a human. It can be a prosimian primate like a potto. Okay? They'll all have a pattern that looks something like this and is actually about the same length, about 29 days. During this particular part of the cycle, the follicles are growing, and particularly in this range, they're growing very rapidly. And they'll start out with a group of them growing. And as they grow toward the middle of the cycle, a lot of them will fall off the wayside. They won't be quite in the right place to get the hormonal signals. They'll become apoptotic, they'll get lost. One or two will get to the point of ovulation. And that ovulation is driven particularly by the estrogen that's produced in this window right here, and by this surge of luteinizing hormone, and to a lesser extent, follicle-stimulating hormone that occurs at the mid-cycle. Now this this surge in estradiol is what switches estrogen control, or the control of LH by estrogen from negative feedback to positive feedback. So this is where the window of change occurs. And so you get the piling up of LH-RH pulses and subsequent LH pulses. So it forms this big peak. And at about this, near the peak time, just after estrogen turns off, you've also triggered changes in these granulosa cells, so they're no longer making estrogen. They switch over to making progesterone. They're undergoing luteinization, formation of the corpus luteum, and they're starting to do it even before ovulation occurs. Only slightly before ovulation occurs, but still before. So you get this crash in LH occurring. So no longer positive feedback from estrogen, but you're starting to see progesterone creeping up, and that's taking over negative feedback onto LH and FSH. So those both go down to low levels that are maintained through the rest of the cycle. During the latter half of the cycle, you're going to see progesterone, and it's all coming from this corpus luteum that's forming. There is in the primate, particularly in human, some estradiol that's also made. If you were to do this in a sheep, what you'd see is that the estradiol goes down and flattens out. And you'd see almost all progesterone, very little estrogen being made. Okay. Now, the phase over here, while follicles are growing, is called the follicular phase of the cycle. Understandably, in the middle, you have the ovulatory phase, or the mid-cycle phase. The period after formation of the corpus luteum is termed the luteal phase of the cycle. So these refer to what's going on in the ovary. The normal length of the luteal phase in a primate is 10 plus or minus 2 days. Okay. If it's too short, it doesn't support fertilization. If it's too long, it also causes potential problems. Okay. Now, this is going on in the ovary, this is going on in the ovary and then in circulation. This is going on in the hypothalamus, pituitary, and subsequently in circulation. But it's not just making the follicle, shedding the oocyte that's important to reproduction. It's also taking that egg, fertilizing it, and getting it to grow during a pregnancy. And so that means that you have to have a coordinated series of events occurring in the endometrium lining the uterus. Okay? So what's happening early on is there's little support of the endometrial lining by the steroids because they're relatively low. And so you get a crash of the lining that was present at the end of the last cycle. Okay? So this is by consensus. What's happening is by consensus the timing of the beginning of the cycle. So it's coordinated with what's going on in the ovary, not with what's going on in the endometrial lining, which is being sloughed. This is actual menses. The first, usually 3 to 5 days of the human cycle, can be up to 7 days as well. Then you've got this growth, proliferation of the endometrial lining. This is under the influence of estradiol alone. So proliferation of the endometrial lining. It's a little misleading here because you don't get a lot of the crypt formation until later. So endometrial lining is thickening. At about the time of ovulation, when you start to see progesterone being formed, you've got estrogen. Estrogen is one of the things that stimulates, is not just growth of the cells, but their production of progesterone receptors. So estrogen has to precede progesterone in order for progesterone to act in the lining of the uterus. And when it does begin to act, it stimulates the formation and deepening of these crypts and the formation of what are called spiral arterioles in the endometrial lining. So you've got blood flow now starting to occur in the endometrial lining. What's happening in these crypts is you've got deposition of a lot of glycogen, so energy reserves. These cells also begin to differentiate under the influence of progesterone, not just by arterial, but they're no longer proliferating, they're becoming susceptible or receptive of potential interaction with a developing embryo. They undergo what's called a decidual reaction. All right. If fertilization occurs, fertilization is normally going to occur within a fairly short window, about 72, no more than about 48 to 72 hours after ovulation. Then that complex, that fertilized egg and its subsequent cell divisions are going to move toward the uterus in the fallopian tube, and I'll show you that in a minute. And they arrive in the uterus to contact the endometrial layer about a week before you would anticipate the next menses to occur. So they're hitting this peak of endometrial development. This slide is also showing you that inhibin, the switch over of inhibin B to inhibin A. This is from the granulosa cells. This is from the corpora luteum. If you did have a pregnancy, this would continue on out. If you have a pregnancy, this crash in progesterone does not occur. It flattens out as well and helps support the early development of the fertilized embryo. But you've got coordination between what's going on in the head, the ovary, in circulation, and in the uterus. So this somewhat chaotic slide is trying to show you the fates of various ovarian follicles. The vast majority of them are going this route, where you get some growth occurring, but in the absence of adequate endocrine support, LH, FSH, estradiol, progesterone, they're going to go on and become atretic. They essentially become scars, okay, within the somatic tissue of the ovary. On the other hand, the minority of oocytes is going to go up this path. And it's going to take about 85 days from the beginning of oocyte growth to ovulation, almost 3 months. So those oocytes, those follicles, are actually going to encounter the hormones, LH, FSH, as they go up and down for 2 months prior to final growth toward antral follicles and ovulatory follicles. But you're going to see the growth I showed you, the formation of the antrum, differentiation of these neural cells, and you're going to end up with, there'll be an interaction with the surface of the ovary and an eroding of that surface. It's almost an inflammatory type response that finally allows the oocyte cumulus complex to be shed, and this remaining rim, along with the theca, to form this corpora luteum. The corpora lutea, in the absence of a fertilized egg implanting in the uterus, is going to involute. It's going to undergo apoptosis itself, and it's going to form its own kind of a scar called the corpus albicans. That is endocrinologically inactive. It doesn't do anything. Okay, I think we've got all of that. Talked about LH and FSH, talked about LH. Okay. So this is another picture of egg development, and this is a nice depiction of the interaction of the shed oocyte cumulus complex with the fimbria, the finger-like projections that are at the end of the fallopian tube. It also shows what's called the os, or the opening to the fallopian tube, and the opening into the lower reproductive tract. So the ovum, the oocyte cumulus complex, is going to be picked up, almost, it's going to be kind of waved in. It's brought in by the fluid movements and by the ciliary movements of the cells that line this structure, particularly during periods of high estrogen content, when these things beat actively toward the ostium of the fallopian tube. So this structure is carried normally in here. Now, what if I blocked this tube? What if I had an inflammatory response to a uterine or reproductive tract infection? So I got scars rather than just normal cells. What happens to the ability of this structure to move the oocyte cumulus complex toward the uterus?
Its function decreases.
Yeah, its function decreases, and what might happen as a result?
Ectopic pregnancy.
Potentially an ectopic pregnancy if this thing got somehow fertilized. If it gets part way up this tract and gets fertilized, and these cells have lost their ability to move the cell progressively toward the uterus, it may end up going retrograde and falling into the abdominal cavity. Now, would that happen in a rodent? See if anybody remembered part of last lecture.
No.
Why?
It's encapsulated?
Yeah. In rodents, you have a covering that goes over the ovary and the end of the fallopian tube. It's a bursa, so this would never get outside that bursa. Okay. In primates, however, it can get outside, and yeah, that's the source of some ectopic pregnancies. The other thing that can happen is, in terms of ectopic pregnancies, it's not just falling outside the fallopian tubes, but it can get stalled in the fallopian tube and go on to develop a structure that can potentially rupture the fallopian tube, and that's a potential source of problem as well. It's potential lethal because you'll get hemorrhaging. Okay. This is other pictures of ovulation, some showing you what's going on in terms of formation of various factors. This is an autoradiograph showing radioactive FSH binding to FSH receptors. Here's a picture you've seen before, and this is a frame from a video that was taken of ovulation in the rabbit. And you see the cumulus oocyte complex exiting the surface of the ovary and coming into proximity of the fallopian tube. This would be a cross-section of this event where you're seeing granulosa cells, neurogranulosa cells, thecal cells. You can just kind of make out the basal lamina here of the follicle, and there's the oocyte and the cumulus. Now, see here. It should be, I'm not sure. These may be hints of one polar body down here. Okay. And then these are just pictures showing you the transformation of these granulosa cells, which are kind of irregular in shape and have a very large nucleus relative to the cytoplasm, into these luteal cells. So these are granulosa cells, and these are luteal cells. You can see they stain very much differently, and this cell is so big that on the same scale as this one, you're missing a lot of the cell, which is out here somewhere. And there's the oocyte, and it's well-formed nucleus and nucleolus. Okay. And this is just showing you some of the coordinated changes in the uterus, oviducts, and the cervix. One thing I didn't mention is the cervix, under the influence of estrogen, makes a watery mucus. It's been described as egg yolk-like. That mucus, which normally exists to try and maintain asepsis in the uterine cavity, so it keeps out bacteria and yeast, that happens to be allow alignment of mucal fibers so that sperm can pass into the lumen by coming in contact with the outer mucus layer and then kind of swimming up through the mucus without too much problem. Once progesterone starts being made, the structure of that mucus in the cervix changes and becomes much more tacky, much more sticky, so sperm have a lot more difficulty trying to pass through that area. Okay, and this is just showing you coordinated changes in all of the parameters. You also see changes in steroids that you can find in saliva and in urine, and amounts of mucus that are being made in the cervix. Interestingly, basal body temperature, and notice that this is a very blown up scale, so it goes 36.2 to 37, just over 37. There is, when progesterone starts to go up, temperature starts to go up a little bit. This has been used for natural family planning, so you track basal body temperature, and that allows a decision in whether or not to have intercourse prior to ovulation. But ovulation occurs right here. Okay. So if you wait until this jump, the horse is out of the barn, as it were. Ovulation has already occurred. Okay. So this peak in basal body temperature is too late to allow effective contraception. It may be early enough to allow fertilization to occur, because that you're still inside the window of opportunity for fertilization. All right. Okay, let me go back one. See if I can go back and say a couple of things. Let me first ask the question. So I've gone through most of this stuff over here. When can a woman get pregnant? During her cycle.
Ovulation.
Just after ovulation? Any other suggestions?
During ovulation?
Pardon?
Like in the middle of ovulation?
In the middle of ovulation, well, she was saying in the middle of ovulation. The endometrium isn't thick enough at the time of ovulation, but it will be in a few days afterwards. Okay. What has to interact for pregnancy to occur? Sperm and the egg have to interact. How long does an egg live after ovulation?
24 hours.
Roughly 24 hours. That's the best guess. How long can sperm survive in the female tract?
5 days.
5 days? Pardon? Around 72 hours for a single sperm. This is where it gets complicated. For a single sperm, it's about 72 hours. But he's depositing 200 million sperm. Okay.
Like 5 days.
5 days?
3 or 4 days.
3 or 4 days? Up to 2 weeks, folks. It's up to 2 weeks because the average is 72 hours. And it's a bell-shaped curve. And you've got 200 million of them to deal with. There are some that are going to be on the extreme. Some won't last 72 hours, and some will last 2 weeks.
So those that last
2 weeks later, she'll get
are
knocked
they
up.
like just as strong as they were?
Okay, what that means is there is a window of opportunity around the timing of ovulation. It begins a couple of days before ovulation because of the lifespan of the sperm, and it extends to about 24 to 36 hours following ovulation because of the lifespan of the egg. However, okay, that window of opportunity is long tails, particularly on the follicle side, follicular phase side, and that's simply because the large population of sperm is going to have a few members that extend that curve down. Yeah.
Are there differences in the health or length of pregnancy or the outcome if the sperm is older when it meets the egg?
That's an active question. Likely is, but that isn't the solved question. Okay, so there's a window of opportunity around the timing of ovulation, and it's asymmetrical, so it's longer on the follicle side than the other side. The other thing I wanted to mention in the female cycle, okay, I talked about 10 days plus or minus, and we talked about 29 days as the normal cycle. Because of the variability in the follicular phase of the cycle, cycles can vary a lot, particularly in the time of puberty and the time just preceding menopause. Okay? There can be a lot of variability. So you can have cycles that are abruptly or that are effectively failed because no follicles ever get to the ovulation point. That means that the next cycle follows immediately, and it looks like the follicle phase is a lot longer. That makes the overall cycle between menstrual cycles long. It may go out to 40 days. Okay. So I'll finish up this harangue tomorrow and get us into pregnancy. Have a good weekend.